Hello, it's Keith here, and this is lesson 51 of the platform-specific series of my 6502 assembly programming tutorials, and we're looking at the Ataris today, the 800 and the 5200, basically the same system from the point of view of today's tutorial. We're looking at sound, and we're going to be writing what I call ChibiSound Pro. Now, ChibiSound was my little simple sound driver, which was designed for very crude beeps and bloops for little Space Invaders type games. ChibiSound Pro is my sort of experimental little extended version of this. The Pro moniker is a bit of a joke. It's based on the Sound Blaster Pro. It's not professional by any standard, but it's a bit better than the original ChibiSound. What it's designed to do is allow us to make simple music that will work on multiple systems in the same way. And by that I mean that I have my own music tracker. It will output a binary file, and that binary file will play on any system without even being re-exported. So I can export for the Amstrad CPC's AY sound chip, and I can play it on the 5200 pokey sound chip, or even on the 68000 systems. So hopefully the music will play in roughly the same way in all systems and sound as similar as possible as can be done. Now, the way we do this is we transfer 4 bytes that will set the parameters. Now, these mimic Z80 registers, so we have 0 page entries marked as H, L, and a DE pair. The H entry is a channel number with bits 0 to 6, and bit 7 will turn noise on or off. The L byte will be the volume 0 to 255, with 255 being the loudest and 0 being silencing the channel, and D is a pitch from 0 to 65535, with 0 being the lowest pitch. Now, these are standardized, and we will send these to the hardware, and then the ChibiSound Pro driver will act as the hardware abstraction and will actually do the job of making the hardware work in a common way. Now, that's all that ChibiSound provides. It doesn't provide things like envelopes, because those aren't very easy to standardize across all the systems, so it's not something that the ChibiSound Pro that we're writing is designed to do. Now, one other thing that ChibiSound Pro isn't itself designed to do is to standardize the actual volume, the pitches, so that the same number is the same pitch on all systems. What we do have though is we have a lookup table, which I refer to as ChibiOctave, this lookup table here, and this has entries that will give the numeric values that we would pass to the DE pair to give the matching tones on all systems where possible. Now, in some cases it's a little bit difficult because the range on some systems doesn't match others, and so I add a transpose option here, which I originally had to put on the master system. So this will allow us to sort of miss parts of the table that don't actually exist, and will transpose the music to a higher pitch, but will allow potentially a range that gives the notes better. So that's an optional thing. Now, we have 2 options for testing. The one we're going to look at today is this very simple ChibiSound Pro test here. Now, if I just run this here, and we're going to run it on the 800 here. Now you can hear, if I just get my oscilloscope up here, you can see we've got a pitch here, and then if I use the joystick here, you can hear and see as I make the number go higher, the pitch will change, and I use this for testing and for calibrating the hardware. If I press the fire here, I can turn distortion on and off there. So as I say, this is just a very simple program for testing the driver is working correctly, and for matching the frequencies, calibrating them for the lookup table here. So that's what I use to create that lookup table with a frequency analyzer. Now, the more important thing is that this can be used for music, and so this is the ChibiTracks test software here. The ChibiTracks is the player, and so here is a little music file that I created originally for my new Chibi Fighter game I'm working on there on the Amstrad CPC, and the file that we're playing here hasn't been re-exported or converted in any way. So as I say, while it's musically quite simple and the instruments aren't that advanced, it will work on all systems without any extra work, and that's what this was designed to do. So that's what that's designed to do, and that's what we're going to be looking at today. Now, the ChibiSound, the Chibi Tracker software, being as its origin is the AY sound chip, we really needed 3 channels. Now, the pokey on the Atari is quite luxurious to us. It gives us a whole 4 channels, which is 1 channel extra, so we have a whole extra channel that we can enjoy. Now, it's very simple, the memory layout. The memory addresses are actually different on the Atari 800 and the 5200. They moved the pokey chip, and this was intentionally so that you couldn't write software that worked on both in different marketing departments, different budgets and things. So they didn't want the profits to go to the wrong department, so they intentionally balked it, which is annoying. But basically, we will just define a a symbol called pokey, and we will set it to the base of D200 or E800. Now each of these sound channels has 2 bytes, one to set the frequency and one to set the noise and volume settings. And so we will just need to select one of these according to the channel we actually want to set. And as I said before, that will be defined by the H byte. So that's what we'll do. We'll also need to set the audio control, and we'll just need to initialize that. So that's what we're going to be seeing in our code. So let's go over to our code and let's take a look. Okay, so this is the file. It's the same file on both systems because, as I say, all it relies on is a symbol pokey being defined and pointing to the hardware. Now, when we start up our system, we will first want to do this initialization, and all that does is it writes to the 8th register within these pokey registers, and that is the general audio control, and it writes a 0 to this, which sets up the noise and it sets the clocks. So that will just set things up in a way that will work quite nicely. Now what we're going to do next is we're going to take the L byte, which is the channel and also the noise state. Now the noise state is the top bit and the rest of the bits are the channel. So theoretically 0 to 127, but we've only got 4 channels, so we're only going to take the bottom 2 bits and we would loop around for any extra channels. Not a problem because, as I say, my chibi tracker in my music is really only intending to work with 3. So the 4th one would probably never be used, but anyway, as I say, we're working with the potential for 4, and we're then doubling that, and that is going to become an offset, and that would be on the Atari 800 D200 or D202, D204 and D206, and of course there is 1 extra register after that. So that is the base for our sound registers. Now the next thing we're going to do is we're going to set the frequency, because that is the first of the registers. Now it only takes a single byte. Now my software is providing a DE pair, but we can't use that, so we're just taking the D part. But the frequencies are actually inverted to what I would use. I want the highest number to be the highest pitch, but this is the opposite way around. 0 is the highest frequency, so we're actually flipping all the bits there with an EOR command before we're writing it to that first register there. Y would be the offset to the channel number, so we're just writing that first one setting the frequency, and then we're increasing Y to point to the second one. Now the second one will set the noise status and also the volume. Now the bits we want to write there will vary depending on the state of the noise. If we want a square wave, we want to set the top bits to probably 1010. If we want noise, then we want to write the top bits as 0. So that's what we're going to need to do, and we're going to do that based on the top bit of our L value. So we're checking that, and if that's a 0, the noise is off, and if it's a 1, the noise is on. So we're loading the B entry here with the profile for the square wave. We're then checking that top bit, and if it's on, then we are setting those to 0, which is defining for noise. So B is now got the correct settings for the kind of sound we want to make. What we want to do next though is we want to combine the volume, because the bottom 4 bits need to be the volume. So that is in our H entry in the 0 page, but that's an 8-bit value, so we only want to take 4 of the bits and we want to shift it to the right 4 times. So this is moving those bits from the top to the bottom, and we're then ORing in the 4 bits that we defined as either the noise or the square wave. So we're combining those together to get the value for the second sound register, and we're storing that there. So that is setting the second register. So that has set both of them, these 2 or whichever 2 relating to the channel that we're actually setting. Now this routine will be called every time we want to set one of our channels, so we only need to set 1 channel each time. And then the final thing here, you can see we've got an update function here which does nothing, and that's for systems like the ZX Spectrum type that will not make a constant sound unless we constantly do some kind of activity, and so that update would be run on those systems, but this one, it's not needed. So there we go. So that is the driver for today's system. Very straightforward actually. So if you like what you've seen, please like and subscribe. If you want to see more of this kind of content, and if you're interested in this music tracker idea, please consider backing me on Patreon, because as part of this I've been writing a piece of Windows software, and I didn't really want to do it. I'm not going to lie, I didn't know anything about writing music software in Windows, and so I've had to spend a lot of time doing that, and I don't actually end up making any tutorials out of that kind of work. So if you want to see me working on that kind of thing, please consider backing me, because it's the only way I can justify doing it. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.